So in this lecture we're going to look at the gas hydrogen and its spectrum and how its study of its spectrum can lead to the knowledge of its atomic structure. If you look at the study guide, questions 11 through 17 and 6 questions are on this topic, and we're going to answer each one in turn as we go through. So question 11 asks, how can the spectrum of hydrogen contain so many lines when hydrogen only contains one electron? So this is a pretty interesting question and a good place to start. So we have a proton and perhaps an electron, and they're perhaps separated by some distance, and that appears to be the model of the hydrogen that we can start with. How can it be then that such a simple system can produce a spectrum that has hundreds? In fact, if you go and look in a book of how many spectral lines hydrogen has, or you go and look at a hydrogen spectrum, there are hundreds of different lines crossing all through the spectrum, all the way from the X-rays all the way out to the radio part of the spectrum. And in the visible part of the spectrum alone, there's perhaps almost a dozen different spectral lines. It seems kind of an odd idea. So the lens through which we're going to look at the hydrogen atom is the lens, I guess that's a joke because we're doing optics and so forth, is the Bohr model. So Niels Bohr was the person who came up with this model, and it's called the Bohr model not because it is boring, but because Niels Bohr is the originator of it. So in Bohr's model, he imagined that the electron can only exist at certain different orbital radii from the nucleus, a bit like the atoms in the planets in the solar system. And each different orbital radius has a potential energy associated with it. And so if the electron is given more energy, it could orbit faster initially, and it would move further out. And so we can imagine that this represents the n equals 1, the lowest energy state, and if the electron is given more energy, it might move out to a larger radius, R2, and have a different value of its potential energy. So potential energy is the amount of energy needed to remove the electron from the atom. So if we keep giving the electron more and more energy, it will move out to greater and greater and greater radii, and at each one it will require less energy to remove it completely from the atom. And at some point, when it's completely removed from the atom, no more energy is needed to remove it because it's already removed, and so when it leaves the atom, its potential energy is said to be 0. Now in Bohr's model, there's an equation which describes the amount of potential energy that the atom has at each different energy level. So let me mention this is n equals 1, this is the second energy level, this is at n equals 3, this is n equals 4, and so on until it leaves the atom. So here's the equation. En, the potential energy of the electron at each energy level, is equal to minus 13.6 electron volts times z squared over n squared. N squared is the energy level. Z is the number of protons. So hydrogen only has one proton, so Z equals equal to 1. So let's try and figure out what these energy levels are then. So E1 is simply minus 13.6 electron volts. E2 is going to be minus 13.6 divided by 2 squared, which comes out to minus 3.4 eV. E3 is going to be 13.6 divided by 3 squared. 3 squared is 9. So this gives us minus 1.7 eV. And we'll probably stop at the next one. E4 is going to be minus 13.6 divided by 4 squared. 4 squared is 16. So 13.6 divided by 16, which is minus 0.85 electron volts. So this is commonly represented by drawing a slightly different diagram than this orbital diagram, and instead drawing what's called the energy level diagram. So here we're going to draw the energy level diagram. So this is typically drawn by drawing a pair of axes. They're not really proper axes in a graph. This one here is potential energy. And we're going to draw the ground state, n equals 1. So the energy of n equals 1 is 13 minus 13.6 eV, so that sets down here. This is called the ground state. Then let's draw a line for the n equal 2 state, which is called the first excited state. N equals 2, n equals 1, so here's our value here from up here. minus 3.4. And the third state is at minus 1.7. So I'm not making an effort to draw a really accurate diagram here, but you can see that the gap between 13.6 and 3.4 is much bigger than the gap between 3.4 and the next one, which is at minus 1.7. And then so this same pattern continues. The next level is much closer again, because it's at minus 0.85. And so you can see in this way that the next level is probably going to be somewhere here. So I'll just draw it in, n equals 5. And then equals 6 will be even closer. And so they're getting closer and closer together. So perhaps by the time we get up to here, we will be at n equals infinity, and our potential energy will be equal to 0. So if an electron starts down here on the ground state, like over here, in the first closest orbital radius it can have, and it's given more and more energy, it will first jump to this n equals 2 level, then it could jump to the n equals 3, the n equals 4, n equals infinity, and at some point it will leave the atom altogether. So the energy required to ionize a hydrogen atom depends on what state the atom is in. So if the atom was in the ground state, it would take 13.6 electron volts to bring it all the way up here to 0 and be free of the atom. So 13.6 electron volts is called the first ionization energy of hydrogen. If it happens to be in a more excited state like n equals 2, the ionization energy would simply be minus 3.4. So whatever energy level the electron is at, that's the amount of energy it would take to ionize that atom and remove it completely. Now, of course, it doesn't have to completely ionize it. Let's say an electron is sitting in a particular energy level, and a photon of energy comes in, or the atom gets hit by something, energy is given to the atom. The electron can be kicked up to any of the energy levels in principle. And just as it can be kicked up there, it can also drop back down again. So one of the questions on this question was, what is the longest wavelength of light capable of ionizing hydrogen in the ground state? So let's imagine here, hydrogen in the ground state. Photon comes in. If this is to be an ionizing photon, the energy of the photon must be equal to the change in energy required, greater than equal to E1, because it's in the ground state, it has energy, potential energy E1. So that tells us that the ionizing photon has to have greater than 13.6 eV, so can we find out what its wavelength is? So let's see if we can do that over here. E phot equals hf, where this is Planck's constant. And this is the frequency. So this means we can use C equals F lambda to find that hc over lambda equals E phot. So the photon energy is required to be this. We know what the photon energy is, it's 13.6 eV. We're trying to find the wavelength. What is the longest wavelength that can actually do this? Let's rearrange to make lambda the subject of the formula. So lambda goes across the equal sign, it goes from divide by to multiply by. Hc stays where it is, E phot goes from the left to the right, it goes from the top to the bottom. And we need to work in joules if we're going to use Planck's constant in joule seconds. So we need to find out what is E phot in joules. So minus 13.6 electron volts, can we convert that to joules by dividing it, I multiply it by 1.6 times 10 to the minus 19. Which is 2.176 times 10 to the minus 19 joules. So that's the number we're going to put in here. So Planck's constant, 6 times 10 to the minus 34 joule seconds. Speed of light, 3 times 10 to the 8 meters per second. On the bottom, 2.176 times 10 to the minus 19 joules. Put that in your calculator. Sorry, that was 10 to the minus 18, wasn't it? I said the right number, but I wrote the wrong number down. Is 8.27 times 10 to the minus 8 meters. So, what is that in nanometers, say? Which comes out to be, lambda must be less than or equal to 82 nanometers. So what part of the spectrum is 82 nanometers lying in? So 82 nanometers is shorter than the shortest wavelength of light that can be seen by the human eye, which is 400 nanometers. So this is in the ultraviolet. So what we've just inferred is that ionizing hydrogen from the ground state requires ultraviolet radiation with a wavelength of 82 nanometers or shorter. So we'll do one more question related to this topic, which is the first spectral series to be discovered is the Balmer series, which corresponds to transitions from atoms ending on the n equals 2 state. So one of these transitions from, say, the n equals 3 to the n equals 2 will radiate away a photon. The energy of the photon is going to be equal to E3 minus E2, and the same is true for any of these transitions. That's how you find the energy of the photon emitted in all of these different cases. The question is, why is it that this series was the first one to be discovered, when you might naturally think that the series ending on the ground state would be the first one to discover, because the ground state is the simplest one? Of course, we've also already got the answer for that here, which is that it turned out that all of the transitions ending on the ground state are in the ultraviolet, so they were not discovered until later when people looked in the UV. It turns out that all the transitions ending on the n equals 2 state are all in the visible part of the spectrum, and so that series there is called the Balmer series, and these transitions ending on the ground state are referred to as the Lyman series. And there's another series, all the transitions ending on the n equals 3 state are in the infrared, and that continues to be true as we go further and further up. So I think we'll end it there.